Hi,
Okay, so good afternoon, everyone. Can you hear me?
Hi, Greg.
good afternoon. Yes,
Okay,
Yes.
thanks. So, welcome to this webinar on reservoir fluid characterization with FluidModeler. Please, let's just bear for another 2 minutes so that we can have more people joining. And then Mr. Lekan, which is our presenter for today, together with Samuel, will start this webinar session. Thank you.
Good afternoon, everyone. And for those joining us from places with different time zone, I'll say good day. So we're going to be having this discussion in the next 1 hour. So be taking us through a new tool for carrying out reservoir fluid characterization and modeling, and that is the FluidModeler. My name is Lekan. I'm a reservoir engineer with Schlumberger. So I'll take us through this following outline, just to a brief overview of the reservoir fluids, the experiments, the PVT-QC, then we'll focus on the tool itself, the FluidModeler, and I will run us through the presentation as how to prepare the fluid and carry out a recombination of the fluid load experiment, then do the characterization of the plus fraction, the EOS tuning in the FluidModeler, and how that can be exported for use in simulators. Then I will run us through a demo, then we have the conclusion and a Q&A. All right, so we know these are the reservoir fluid classification ranging from dry gas and wet gas, gas condensate, volatile oil, black oil. And in some cases, we call some fluid the near critical fluids, and those are kind of fluid that actually need some proper characterization and modeling as regarding to using them in reservoir simulation. Yeah, on the side of this presentation, we see the phase envelope for coming about the different characterization of the fluid, right? So, and one major thing, just like any thermodynamic substance, for you define the state of such substance by knowing the temperature, the pressure, and the volume it exhibits at those two conditions. And vis-a-vis the word PVT, those are the key parameters that actually determine the state of the fluid, which is also the driver in classifying them by the behavior of their phase envelope. And getting out reservoir fluids, we know that the two major approaches is either we sample downhole or we take a surface sampling, depending on the situation we have in the reservoirs. Right, so on the various experiments being done, this is just to highlight some. I'm sure there are other experiments being done that we didn't capture on this slide. But of course, the common one are the constant composition experiment, CC. Then we have the constant volume depletion, CVD, essentially for the compositional fluid. Then we have the differential libration, which is commonly done for black oil. And we have separator experiments, slim tube experiments, and all of sorts. So these are the various experiments that are carried out in the laboratory just to be able to see how the reservoir fluids will behave throughout the history of depletion of the reservoir, and sometimes even to know what will be the nature of this fluid when the conditions in the separator change. And that way we can be able to impose all of this on the simulator to see how the fluid actually behave when the reservoir goes through the pressure gradient and the temperature gradient. Of course, on the isothermal assumptions we have in most of the simulators, we practically assume that the temperature in the reservoir is isothermal, but we also know that in some scenario we could have a multivarying temperature system whereby you have different reservoir fluids at different temperature. But in this case now, we'll just be looking at the case of, for instance, this cartoon I'm showing us is just on the assumption of we have an isothermal system. We know that for the fluid to move from the far reservoir to the sand face or the well bore, it will transverse through a pressure gradient. And moving from the sand face to the surface, it will also go through a temperature gradient, and the pressure gradient is constant all the way to the stock tank. And this way, the behavior of the fluid will definitely change, and we should be able to actually model that. And which is why it's essential to be able to have a tool that will be able to give us the behavior of the fluid over a wide range of pressure gradients and also temperature. And just down here, we'll see just the picture of some of the PVT labs and the equipment used to carry out the experiments. Okay, here, so it's just to bring to perspective more in terms of the previous cartoon I just showed, looking at how we proceed in carrying out the fluid characterization or fluid analysis, whether we're doing a bottom-most sampling or a surface sampling. Now, the first thing we do is when we sample whether bottom-most or surface, we want to do a sort of restoration or validation. That's in the lab. You want to check whether the opening pressure compared to the reservoir pressure and the covering pressure at the field. And even for the surface sample, we do the same thing. Then we carry out the saturation pressure analysis. That's talking about the CCE experiment. In some instances, this is also carried out if you want to know the different saturation pressure by flashing the fluid. Then after flashing this fluid, the next thing that is done is to carry out a recombination for surface sampling where a liquid is sampled separately and the gas is sampled separately. There is need for a recombination. And after that, we have the reservoir fluid sample. And that's, if you look at this cartoon, for a bottom-most sampling, there is no need to carry out all of these recombination. There is no need for recombination because it's in a single phase, right? So the next thing we have there is a fluid sample. Compared to when we do a surface sampling, we'll go through all this validation, saturation pressure, and the recombination of it. So now we have the reservoir fluids, and the next thing is to now identify, is the fluid gas, is it volatile oil, or is it a black oil? Of course, this word volatile will be taking it with respect to near critical fluids. Then we have the black oil, which is a stable oil that it's just in the liquid phase. Then we have the gas that is purely in gas phase. Then of all these type of fluid, we know that the experiment common to them is the CCE experiment. Then for the near critical fluid and gas, depending on whether it's wet, right, we do a CVD. But I know in some school of thought for a dry gas, there is an assumption of you actually modeling it with a black oil simulator. So for black oil, we do a differential libration. Then common to all of this fluid is the separator test, because all of these will definitely have behavior they exhibit in the separator. And we have further studies one can do, maybe going into EOR, you want to start doing some gas injection or chemical injection. So we want to see, okay, what could be the minimum mixability pressure, the slim tube experiment. Those are the classes of the advanced studies. Okay, so talking about the PVT QC, now even before going ahead to want to carry out experiments, even in the lab, we want to first know, okay, what kind of sample? Is it surface or it's a subsurface sampling? At least for a surface, just like what I showed previously, we know that we go through some recombination and want to know what is the field GR or the separator GR as at the time of taking the surface samples. Then for the subsurface, we want to be sure that the reservoir pressure is not at or below the fluid saturation pressure as when the sampling is taking place to ensure the representativeness of the fluid, and which actually asks the question whether it's in a depleted reservoir or not. Well, being depleted now, it's not to say that sample can still not be taken, provided the reservoir pressure is still far above the bubble point pressure or the dew point pressure, depending on the reservoir in question. And in that case, we also be looking at what's the conditions in the well. Are the wells properly conditions, and do we attain equilibrium before taking some of this sample, most especially for the surface sample? Then we carry out some quantitative tests or check on this fluid, looking at the material balance. That's the K plot. And the K plot is essentially looking at the composition in the gaseous phase compared to the liquid phase, and you expect it to give you a linear relationship. So deviation from this means that there could be issues about the fluid or during sampling, equilibrium issue during sampling. Then we have the qualitative check also, that's the Hoffman-Crom curves check on the fluid, just to see that in this case we're looking at it in combination with the K plot to see that there is consistency ranging from the I component of the fluid, that's talking about the C7 plus down to somewhere around the C4, and the lighter end if we have consistency in their composition distribution in the fluid. Okay, so now I'll be talking squarely on the FluidModeler, and FluidModeler is actually the new fluid modeling tool by Schlumberger. So previously we have PVTI, but FluidModeler, it's an advance and it's an improvement on PVTI. So, and it's actually a fluid modeler that is having all the state-of-the-art algorithm we can think of in terms of how we now carry out fluid modeling. It's totally different from what we used to know, and it's bringing more flexibility, and it's becoming more of user-friendly, and also making us to interact more, unlike what we get in the existing tool before now. So it actually is designed to model the standard PVT laboratory experiment and down to carrying out some analysis as regarding the complex EOR we now know are being carried out in fields worldwide. Then it has its optimization tool, and the workflow is actually well guided this time around, and we see that it helps to reproduce the same fluid behavior every time you run it, because it gives you a best fluid model characterization. And at this point in time also, some of the things we don't have before, comparing the phases envelope on the fly, you can actually see how your fluid phase envelope changes when you go about regressing the fluid, and compare with what you start with and what you finally have as the regress fluid model. Like I mentioned earlier, it is a new generation PVT package. And in terms of usability, it's very user-friendly. And the workflow we have in it now, it's in such a way that we can actually track all the activities carried out at different stages of the fluid regression. Then in terms of science and performance, the accuracy of this tool, it's actually very rigorous, and even the tuning, it's rigorous as well. Then it has a robust optimization tools, ensure to have your fluid model actually being well EOS matched. Okay. All right. So let's continue. Please let's remember to mute our mics. Then it also has superior performance, and that's because of the E300 flash we now have in the PVT2. So all the things we know about PVTI in terms of edge, this is coming at a greater step to that. So in terms of optimization and performance, it's faster. It's something, unlike the issues the previous PVT tools do have, you don't experience that in PVT, in this FluidModeler, because of the optimization in its performance. And also we can keep a trail on the fluid. Keeping a trail in the sense that when you do a fluid, let's say you do your C7 characterization, we can actually see the fluid before the characterization. That's the original fluid still being in your model, and you have a fluid that you've characterized. So you can actually compare the phase envelope, and should you are not satisfied with the characterization, rather than starting all over again in loading the fluid, you have the original fluid being there. So you can just make a copy and rerun your analysis. So that builds efficiency into this tool. And also you can check the fluid you tune compared to the one you didn't tune. It gives you the privilege to actually retain your original fluid. Should you tune and you're not satisfied with that, you don't need to go back and recreate everything again. You just have the original fluid there. So it gives us the room to be able to create different fluid types and test out different scenarios, EOS tuning, and see which one is actually giving us the behavior that the fluid actually should have. And just before I leave this slide, prior to now, this FluidModeler is usually available on Delphi, but now it's also on premise, which means that we can actually run it on our local system. So the approach in building this FluidModeler, that's what we seek to achieve with this tool, is to ensure that first we have this integration. We have this integration and reproducibility of the PVT analysis carried out on the fluid. And the usability also, it's something that's put in mind in coming up with this fluid model. We're talking about the fluid model chain of custody, and whereby we can access all the different fluids in the same FluidModeler project. And the user interface is actually greatly improved. It's just guided, just like what we have in Petra environment, whereby you perform this experiment, this task before you go to the next one. And that is actually well spelled out on the user interface of this tool. Then on the science and performance, of course, I mentioned earlier, there is a very robust engine running at the back of FluidModeler in terms of the optimization. So it actually helps you to optimize even during the EOS tuning, which we'll see during the demo. And also in terms of different EOR experiment data, you can actually carry out all of this in this tool. And the turnaround time, that's the time to actually carry out some of this analysis is very, very fast. It's very, very fast compared to what we used to have in the past. Okay, so I'll run us through some of the functionalities we have in the tool, like I've also alluded to in the previous slide. So the user interface is there. Then we have the isothermal compositional gradient, and this can actually be carried out in this FluidModeler. Now I'll focus on the EOR. We see on the EOR now we can actually carry out a swelling test. For instance, maybe you want to do a swelling test of dissolving CO2 in the fluid. That can be done. And you want to do a swelling test of dissolving maybe C1, injecting back the hydrocarbon gas into the fluid. And you want to come up with the mixability pressure, the minimum miscibility pressure, that can be done there. And also the ternary diagram, you can also visualize that in this tool. So all of these are built into this tool to give it that robustness and superior performance, even enabling us to achieve the current advanced physics in terms of fluid characterization. Okay, so now I'll be taking us step by step through the interface, and the first thing we have here is the user interface. So from this point to this side of the user interface, the first thing we see here is the setting up the new fluid. And just to mention, it's very flexible in dealing with now, because all of these you can actually prepare your fluid, your data in Excel, and by matter of just doing a copy and paste, you can replicate the same thing into FluidModeler, and which I will see also during the demo. It's very easy to interact with. Just set up all the necessary data you need in Excel, and you just you can do a row by row editing, or sorry, column by column editing, whereby if, for instance, I notice that, okay, my molecular weight, the one entered, is actually not what I want to use, and you just go back to your Excel sheet, make a copy of that and update this, and the calculation will be redone in such a way that it will reflect the molecular weight you updated your fluid with. And also to mention, on this side of the tab, it keeps trails of your fluid. You see, in the case of whereby we're having the oil, the gas separately coming in, we can have see it, this is the oil, the gas, and the recombined fluid. And it keeps this, even when you are carrying out your characterization, you have all these fluids still intact, so you can go back and recreate that. So when you create the new fluid, you add it in and you see your phase envelope, which is what we're seeing on this side. Then we can actually track the history. So what I was saying is, so coming from the new fluid, now we can edit the fluid. Once you create your new fluid, all of these become active. You edit and you can export. These are the export options. Let's say the analysis had been done for, let's say you did the project in January 2018, and for some reason want to revisit the fluid. This fluid history can help one to retrace what are the activities carried out to arrive at the final fluid that was exported, which is more like keeping track of all the activities done on the fluid to get to the final stage. And this hasn't been before in the previous two. And this is where we run the different experiment. When you load the experiment into this FluidModeler, what we see is that the FluidModeler will generate the same experiment and will compare the outputs from the experiment to the actual data. So this is where all of those activities are taking place. Now, on this side, we can group fluids. Now, the fluid grouping thing actually becomes handy. For instance, let's say we have a fluid we want to EOS match separately, and we also want to carry out, let's say, a swelling experiment on another fluid by bringing in maybe CO2 and bringing in the hydrocarbon gas to be injected into this fluid. So we can group all of these fluids together such that all the analysis that will be carried out will be applied to all the fluids that are in that group, rather than having them individually. And prior to now, we don't have such functionality to carry out. So it helps us to have, for instance, let's say we have two fluids and the composition are the same, but we want to carry out a regression on the two at the same time. Maybe now I have the gas and I have the actual fluid. So rather than doing separately on the actual hydrocarbon fluid, then going back to the gas, I can group them and carry out this analysis on them as a group. Then the C7 plus characterization, where we do the splitting and the lumping of the C7 plus. Then this is where the tuning is going to be done. This is where we tune the fluid and the recombining functionality. coming back to decontaminating the fluid, should we know that there are some level of contamination in the fluid sample, that can actually be done around there. Then these are actually the grids of the components and the binary interaction of the phases, the values. Then we can have the different stages of experiment. Then to see the various plots, this is actually where we can see all the various plots. We can see the phase envelope, the ternary plot, the experiment plots, and this is how the OTABs are arranged, and that's we go through down to when we can actually come to exporting the whole fluid to a sheet and see how everything looks like. And this is all about the FluidModeler interface. Okay. So preparing the fluid, like I mentioned earlier, to start loading the fluid into our FluidModeler, this is where we start from. That's the new fluid. And when that is done, it will open this table. And this table is just going to come with a blank. You just have some of these, all these components won't be there. So you just open a row for you. And why that is because all of these components, you have it coming from your PVT experiment. So if you had prepared them already in Excel sheet, or the naming you've given onto them and all of that, even the molecular weight or the mole fraction, all you just need to do is to make a copy of that and you populate that into here by just the Control C and Control V. And that will bring in those components and their molecular weight here. And once you come to the aspect of setting up the fluid, where you edit the fluid by defining the reservoir temperature of your fluid, your reservoir pressure, and also setting up the units, which I will show us during the demo, then we can come here and set the equation of state to be used. So the Penn-Robinson, the 3 parameter, the 2 parameter, the SRK, all of them are there. And you can make a choice of which equation of state you actually want to fit your fluid with. But for usually you can start with what you have as default, but when you come to tuning, this can actually be changed and see how best it fits to your fluid. And the same thing for the viscosity model. We have the various models that fit the viscosity, so you can make a choice of which actually fits your fluid. And once all of this is set and you copy paste the components and the molecular weight fraction from the Excel sheet, and by just clicking on the apply, it will calculate the remaining part for the fluid. That's the FluidModeler will calculate all of these normal boiling. And just before I leave this slide, we'll see all the one that is showing us like a pencil is actually telling us that the value this component is having is different from what is in the library of FluidModeler. And this is another good edge of this FluidModeler, because if, for instance, what you have from your fluid in the lab is saying that the value of C3 is 45.2, but in the library it's, let's say, 45 or 39.99, it's not going to overwrite it with the library value. It will retain the value you already have from your experiment, because by the time you copy and paste, once it doesn't match the library value, it changes it to this pencil type. Otherwise, it will leave it as a book, which means that it's consistent with what is in the library. Right, so this is another very good functionality of this modeler. Of course, for those of us that we've done some EOS fitting in the past, most especially for surface sample, we realize that one of the restrictions we have is in terms of the recombining GOR, because some of the tools, you just have to work with what has been recombined from the experimental analysis, and that we use to just run the experiment. But now you have the function, you have the flexibility of actually overriding that, of capturing some of the concerns around the GR, because in this tool you can actually carry out the recombination by just loading the gas composition, the oil composition, specify the separator GR, and you carry out the recombination, and you can compare the phase envelope of the recombined fluid to that of the gas alone and the oil alone. And the recombination can be done based on the volumetric, mass, or molar mass. That's depending on the information available to you. Then this is just loading the various PVT experiment. That's talking about the CC, the VL, the CVD, or the DL, all of that. So just the same way the components are prepared, we can actually load the experiment after preparing it in the Excel sheet by just copy and pasting the experiment as we prepared it into this FluidModeler. And the beauty of it also is that we can move the row by just dragging one row to the other. Just press down your mouse and drag a row to the other side based on how you want the row to appear. So all of these are the flexibility this tool has, and that you can actually do everything you want to do in the Excel, then just bring it in here by a matter of copy and pasting, and visualize even the experiment you've loaded and see how it compares with the data you have from your experiment. Yeah, so I'll talk about also the C7 plus characterization. So we have the Whitson function in terms of splitting and lumping. Then one point I will make here is that in these two, you can actually do both the tuning and the lumping, the characterization of the C7 plus together. The two can actually give you that edge to characterize your heaviest components, at the same time proceed into tuning it without having to do this separately. And that we can see also during the demo. Now the EOS tuning. So on the EOS tuning, like we know, we tune the viscosity separately, and in the EOS tuning part of this tool, that is actually being done. So here, these are the tuning types. So you tune the equation of state first, then after that we do the viscosity tuning. But like I mentioned in the previous slide, when I said it can actually carry out a characterization and tuning at the same time, is by starting with the bulk tuning. And this will help to tune the molecular weight of the plus fraction, and also give you the option of splitting and lumping it back depending on how you want to do it. So from there, it's tune the C7 plus fraction, then after which you then progress to the equation of state tuning. Then from there, you progress to carrying out the viscosity tuning. And at the end of the day, you'll be able to visualize, even on a very interactive and visual front, of how your tune parameter compare with what the model is giving you. That's your actual data to the tuning from the tool itself. And also in terms of weighting, how the weights are distributed over your different components, you can see them on a pie chart as we see here. So like where I am now, the weight of my saturation pressure, it's somewhat almost the same as what I have on the CC and the rest. But when you come to this side, we can see that I'm having more like equal weighting on the saturation pressure and the density, and the same way. So on the fly, we can be seeing how the distribution of the weighting in achieving the EOS matching. And also after the tuning, you can actually view the, or during the tuning as well, you can view the objective function, how the objective function is being minimized or some or being optimized depending on the direction of the regression. So the next thing I'll do now is to run us through the demo video. I'll be taking us, just telling us how this is being done. Okay. Sorry. Okay. All right, so this is the interface of the FluidModeler, like I mentioned. So now I'll create a new fluid. And so from the experiment, before even loading the fluid, like I mentioned, you can prepare all your fluid like this. The information for your fluid in the Excel sheet, the composition, the CC, the DL, and the separator test. So having prepared all of this, the next thing we'll do is just to bring all of this from Excel into FluidModeler by just copying and pasting it. So create the new fluid. So this is what it will just show for us. Then we come here and set the fluid property in terms of the reservoir pressure. So we can name the wells, we can give the field names, but here we just set the reservoir temperature. So that's setting the reservoir temperature and the reservoir pressure. So we now go back to the Excel and just take all the components. Then we ensure that the tabs are aligning with what we have on the Excel so that when we bring it in, everything sits where they ought to sit. So this is looking at the spreadsheet, and these are the components. So just copy them, then load all of these experiments into FluidModeler. Just select that, the Control V, we bring everything in. So like I mentioned, now the icons are different because the C3 is actually different from what is in the library. So we can see what we have here now is just loading the molecular weight. So we load the mass fraction of this fluid. So even from this, you can see this is more like a role action. Just copy that role alone. So with a Control C and come to the row, then we do a Control V. So it will populate that row and compute the mole percent and then calculate the boiling point. So on the model now, like I mentioned, so we have the equation of state, and that's for the viscosity. Then we turn on the temperature dependence of the volume so that we can make use of the vcrit to regress also. So all of these are what we can change depending on the fluid. So we can calculate the component properties now, and that will fill out the red area. So we accept this now, then we go back. So before we go on here, we're bringing in even the gas because we'll be doing a recombination. So we can just make a copy of the existing fluid, then override the composition. So we can rename it and call this one gas. So rather than recreate, starting the process all over again, then we copy the gas molecular weight and we use that to override what we have in the oil. So that will change it straight to what the gas is having. Then we'll be having a gas. Then we calculate the components. So now we've been able to bring in the oil and the gas. So the next thing I would do is just to recombine these two fluids. So you can just select the two fluids. That's shift You press down the shift, then select the two fluid, then we open the recombination, and this is the workflow. So that will map the gas and the oil together. Then the next thing now, like I mentioned, we have the option of volumetric, mass, or molar. Then we do volumetric because we have the information of the separator GR. Then we set the separator GR, the separator condition as at when those samples were taken, then the standard condition of the fluid too. And that you can actually prepare in your Excel and just come do a copy paste or write them directly into it. So we'll be filling the GR, the separator condition, and the standard conditions of by the time we're taking these samples and recombine the fluid. So this is just ensuring you map your unit. Just take care of the units. And the next thing, we accept it. Then it will create the recombined fluid, which we can see under there. And that's the recombined streams now. So we look at the phase envelope of the oil, the gas, and the recombined fluid. So once you select the three and you press on the plot, then you click on the phase envelope, it will plot the three. As the guy, this is the oil, and the big envelope is for the recombined fluid. And you can plot the fingerprint by right mouse. By doing a right mouse clicking on that, and it will show you the fingerprint of all the fluid. So the next thing we'll be doing now is to load the experiments. So the experiment loading is similar to how we loaded the fluid. So it's just going back to the spreadsheet and we'll be adding the various experiments we want to load on the recombined fluid by just right-clicking on it and select the experiment. So for this DCC now, we'll see that we have pressure, relative volume, liquid compressibility, and density. So we just ensure that the columns in the FluidModeler are rearranged in that same way, so that when we do a copy and paste, everything sits where they ought to sit. So this is just by dragging to ensure that the column are the same as what you have. And you can do addition or removal of column by just selecting the icon there. Then the one you toggle on will appear. The one you toggle off, we remove from the column. And we make sure that the units are consistent with what we have in our data sheet. Then we'll just do Control V and Control C and Control V. So we can look at the simulated experiment. By running the experiment, then it will do the simulation. And we can check the simulation side by side by toggle on these options there. So we can see how the simulation results and the actual data compare. But this can also actually be seen too from a plot. So the approach of loading the CC is what we use in loading the other experiment. That's the DL, the viscosity, and the SEP, which are already in there. Now, the next thing we want to do is to tune the fluid. And now to tune it, we'll be going through the flow of tuning the bulk first, then do the EOS and the viscosity. So once you select the tuning, And what we want to tune is actually the recombined fluid. And the bulk experiment, the bulk tuning. So we start with the bulk tuning. So like I mentioned, so you can do a tuning and serialization, and that's what we'll just be doing with this. So these are the model for carrying out the tuning. So all of the correlations, this we can change depending on the degree of tuning we are having, maybe after we've tried the default. Then on the serialization, we can select what we want to serialize. If it's up to C20 for us, we'll carry the C20. Then we can specify the number of pseudos. Then we accept. So now we have this. So we want to regress now. So this is where we set the weight. So we want to regress on the PSAT by adjusting the molecular weight. So we just add the weight of 2 on the saturation pressure, then the DL or the separator experiment, we can set the weight on them 0 because we don't want to tune them now at this stage. We tune them under the EOS. But the experiment we are regressing on now is the CE and the PSAT. Then we can see now that as we are adjusting the weights, the pie chart is showing us which one is adding more weight than the other. So what we do now is under here we see the tuning option, then we click on the tuning, and it will be showing us the degree of tuning like we see. And this is looking at the objective functions of the level of tune we have. We can see the observed is at 142. Now we started at 130 before we tune. Then after tuning, it's taking us to 138. So we have regressed on the C7 plus molecular weight. Then we can accept this. Then so we carry on that to carry out the EOS matching, which we further regress to ensure we get a good match on the PSAT. So it creates the tune model, and on this tune model, we continue tuning on it. Thus, we go to the EOS tuning. And then we tune on the equation of state. So now we can set the DL, the CC, and the PSAT. But the separator will just make the weight of the separator less here, depending on how you want to do. But this time around, you can add weight depending on the level of tuning. Of course, these are iterative. And now we are distributing the way we're seeing that on this pie, how the weights on the various experiments are being done. So the next thing we'll do is to now, on the different component, we want to select what and what we want to regress on. Now, in the past, what we do is setting up, maybe for instance, just 111 in some cases, but here, it's less imposing. So we can decide to nominate different parameters as our tuning parameters. Now, if you notice, in the previous one, when you label even the eccentric factor to have the same label as critical pressure, it flags. So now everything is unique. It's having its unique identification so that by the time we're regressing, we can track the way the regression is progressing, and we track which of the parameters are actually being regressed more. Then we can actually also regress on the binary interaction. That's for the CO and the CO, that's the carbon dioxide, the CO2. We can do a binary interaction regression on that and on C1, because those are the two that could be affected with the heaviest components in the fluid. And now we can actually nominate each of them uniquely to see how that performed. Then we can now tune the fluid. And here we will see how the objective function is being minimized as it's tuning the fluid. And when it's done, it closes up that dialog box and it shows this. And we can see the level of matches now. We see the saturation pressure, it matches to almost same value. And we see on the objective function, we've seen it very minimized. And compared to the other experiment, the level of match we have on the CCE, the DL and co. Then we can see the level of match we are having based on the EOS matching now. So the red is actually showing the match. Then we can see the DL. So these are the tuning. The tuning is actually the one in red, but where we were initially is the blue. And we can regress further by going back. If let's say the level of the match is not satisfactory, we go back and regress further until we get a good match. But here we just accept this. Then the next thing is to regress on the viscosity. So regress on the viscosity. So here we just follow on the workflow. Then we set the weights. So we have the DL and that of the liquid viscosity. So then we nominate the parameters to regress on for the viscosity. And that's the critical volume. So having nominated this, then we tune the fluid. And we can now check the level of match we have on the viscosity and the rest of the experiment. So this is the viscosity match. The red is the actual regression. And that's how we run through the EOS tuning in FluidModeler, and there we can accept this, which is actually also very good in terms of being guiding us to progressing on the EOS tuning. So now, having done the match, we can export, and we just right click on the experiment. On the fluid you want to export, and go there and say you want to export, depending on the types of formats you want to export. You can export it as a PV or a black white table, and you can export the equation of state for a compositional fluid. And just like in the usual way, we can set whether it's live oil, dry gas, live oil, or wet gas. And we set the temperature. Then once that is done, the standard condition will bring the separator. Then it will export the fluid. So we nominate the experiment we want to export. Then the next thing we do is just perform the calculation, then it will export the experiment. And this is giving us the plot of the PVT, and the export is already in a file that we can now load into the simulator for the experiment, for the simulation. And now that is done, we can save the model, and we can also carry out a different analysis, the slim test and all of that. So all of this can be done. This is just showing us how we export the fluid and where we save the exported fluid. And this is actually showing how the table looks like from what we exported. So on the demo now, and that's all about the demo, just taking us all the way from preparing the fluid and doing the EOS tuning on the basic black oil fluid. Now to just take us through the conclusion, we've seen the reservoir fluid overview, and then we looked at the PVT experiment and the QC done. Then we've seen the FluidModeler overview and also the demo as even down to exporting the fluid. Then we know that fluid data is actually one thing that also unites the different disciplines in the subsurface. The surface guys, they need the fluid. The subsurface guys, they need the fluid. Even the geologists, the information of the fluid also help them to know some of the characterization they do in terms of maybe fishes and even saturation distribution. So it's a very key data in the reservoir management and even in the subsurface study. And so at this point, just before we say thank you for listening, I just want us to know that after this webinar, the next webinar we'll be having is going to be on the 12th of August, and that will be on the SCAR workflow in TechLog, and how does that relate to carrying out a SCAR analysis from our SCAR data and fixing that to a SCAR model. And also the link down there is just for us to give us your feedback. It takes averagely 5 minutes to get the feedback form filled. Please give us your feedback so that we can serve you more better. Thank you very much for your time.
Thank you so much for that interesting presentation and the demo. So I looked through all the questions on the chat window. It seems that they've been answered. But if you have any question, if anybody asks any question that you want us to cover, please feel free now to unmute yourself and discuss. I say that, Charles, you want to see the compositional gradient experiments. I mean, we can arrange another section just to show you. Very easy. You just add the experiment and define the depth. Then automatically it will generate the component that you want for you. And we can see the advantage of the FluidModeler, the flexibility over the PVTI, those of us that we've been using the PVTI before. Particularly, you see the transparency when you are doing tuning of the equation of state to the experiment that you've got from the lab. You see all those visualizations to help you to see the progression that you are making with respect to the tuning, and also the transparency in terms of the parameters that you are actually changing. You can see the range very clearly. You can change that. So it's just amazing the way you do it. And once you do your characterization, you can either export it to PVT table like Lekan demonstrated, or to the equation of state parameters if you want the compositional module. And you see how we've created the pseudo component for the heavier component. Schlumberger has spent a lot of time trying to improve the PVT package and bring something to the market that will really address the modern issue on the fluid characterization. And that is the answer that FluidModeler has come to present to the market. So I would really encourage you, if you want to have a demo, or if you're considering a PVT package now, this is what I would recommend. More advanced than PVTI, definitely. So thank you so much for that. Nelson, over to you. I see that you have a question for us.
Okay, yeah, the question I have is, you know, at the stage of once you enter your composition and all the things you want to enter, then with your temperature and reservoir temperature and pressure in PVTI, you can estimate the fluid properties like the GOR and all that. In case, assuming you don't have maybe any experiment done. So I don't know whether it's possible to do that same one here.
So,
Yes. What you asked, Nelson, can also be done in the FluidModeler.
Okay.
Yeah.
Okay. So, okay. Thank you very much.
No, you're welcome. Thank you so much, Nelson. Any other question? I mean, feel free to ask before we end the call. I think we are really, yes. Please go ahead.
Hello.
Balate, correct. Yeah, go
Yes,
ahead, please.
Balate, yeah.
Yeah, I would like to know about the availability of this tool. Is it available just in Delphi, or we can have it?
No, you can have it as a standalone now. Lekan also mentioned that when he was presenting. Initially, it was going to be just a DeFi solution, but because of people who are still not yet on DeFi, we want everybody to be able to use these very fantastic products. There is no point depriving people from this. The market has been waiting for this for long, to have a package like this that can help with the characterization of the fluid in a very flexible and robust way. And based on that, we roll it out. You can have it as a standalone version or a DeFi version. So depending on which one you want, you just have to reach out to your account manager, reach out to any of us to make sure that you have it on your workstation.
Okay. Thanks.
Yeah. Any other question or contribution or comment before we finally end the call? No, thank you so much, Angela, for your feedback. We really love that. Thank you, Obi. Thank you, everyone.
Yeah.
Erika.
Hello, Sam. Can I?
We have question from Essay. Please go ahead.
Okay. Thank you very much, and thank you, Sam.
Yeah,
I don't know
you're
if,
welcome.
if my question is actually in line with the last speaker, but I'm just asking. Lovely too. We are happy that we have this now. Is it possible for us to have like a demo license for some of us so that we can actually give a trial, then convince our management for us to go for this new software?
Sure. I would say sure. What we need to do is let's take it offline with the account manager for your account, and you will definitely get a demo license. We'll get you approval for a demo license.
Okay. Thank you very much, sir.
Yeah. Thank you.
All right.
So I have a question from Obi, right? Okay. Lekan, you if you want.
I think Papa is raising his hand. Please go ahead, Papa.
Yeah, hi. Thank you for the presentation. So I have a question regarding the exports of your fluid model post characterization into, say, Eclipse for modeling. I've tried doing some fluid characterization, but then I've been having some issues with the exported plots, especially with BO and RS above the PSATs. We know how the classical BO and RS plots are supposed to look like, but then sometimes when you do some exports, you can have a sort of distortion above the PSATs. It doesn't follow a straight line or a normal trend. You have a distortion above the PSATs. I don't know if you have any idea about how to correct these tables before importing them into.
Lekan, do you want me to take that?
You can go ahead.
Yeah.
You can go ahead.
So, Papa, coming to, let's say, for instance, your solution gas oil ratio, which about the PSAT, you have it to be a constant value. And we know that the simulator has a requirement for a monotonicity of the table that you are bringing in. So what you can do if you really want to have such appearance is that so that if you go above, you understand exactly what you want to do. You can actually make a little bit adjustment. There is a way we do it, especially if you perceive that your convergence issue is associated to that. So you add one more point to that table such that it shows a very large change in pressure, but a small change in that value. So it will be relatively close to being that horizontal behavior, that constant value that you want. And it's a way of tricking the simulator to make that happen. That is actually what you can do. you can let me know if you have such a table. Send me an email. I show you how to do that separately. Coming to OB,
All right. Thank you
I
very
see.
much.
You're welcome. I see a question from OB on the chat window. You say if you have a characterized fluid, can you extrapolate the same fluid to a different? That is coming back to the COMG experiment, whereby you have the composition taken at a certain depth, then you can actually translate it to another depth. You know, honoring the thermodynamic state of the fluid. So it takes it back to any depth that you want, and it gives you the compositional information in that depth, which helps to compare with maybe if you have another sample there to know whether there is actually different compartments or whether it's the same fluid, that what you are just getting is the difference in the composition is just due to the impact of the thickness of the reservoir, the gradient. So you can do that in FluidModeler. You just add the experiments, basically, because the demo that Lekan did, because of connectivity issue and everything, he already pre-recorded it. He just played through and explained. Otherwise, he will have shown you right away. I will have asked him to show you the COG experiment and just add it. Once you add the experiment, it's very easy. It will only ask you for the new depth. And you can have several depths listed. And that's all. And it will generate the composition for you. Okay, Nelson, another question. Is that okay, Obi, before I move on to Nelson? Hello?
Yes, Sam.
Okay.
That's good for me. Thank you.
You're welcome. Thank you so much. So, Nelson, please, over to you again.
Okay, I just want to. There's something that happened one time in one of our fields. So we had a reservoir that had a gas cap. So we tried to take a bottom hole sample. So, but we couldn't take bottom hole sample because it had a gas cap, the GR was so high. So, and when they now took surface samples, they went to recombine it. So the question was like, what are you now going to recombine it to, because you don't know the gas oil ratio. So we now decided that we're going to recombine it to the bubble point pressure, since for it to have a gas cap, then the bubble point pressure should be the reservoir pressure. You understand?
Yeah.
Okay.
Yeah.
So now in this FluidModeler, is it possible to do something like that, to recombine it and maybe fix the bubble point pressure when you are doing your recombination?
Yeah, so, at that bubble point pressure also, we'll know the maximum GR there, or the GRs at around that time you took the pressure. I don't know if that is available.
The issue is that the GRL was not reliable because, since it has a gas cap and it was drilled into the gas core, we didn't know, nobody really know the actual GRL, because,
So
we just started producing gas. Yeah.
Yeah, this is actually a concept-related challenge rather than the application. In terms of the application, yes, because if you provide the geo, whatever geo that you have, whether it's right or wrong, the application will recombine at that value. So that is not a problem with the pressure. So now it's a matter of making a decision that since we have uncertainties around the geo that you have, because if that is wrong, your recombination will be wrong. So now you are trying to take it to the bubble, the saturation point.
Yeah, knowing that it has a gas cap, then
no,
the
I got
pressure.
it. I got the concept actually what we are trying to do. So that can be done in PVTI. FluidModeler. FluidModeler can do. If that decision you think it will give a representation of your fluid system, then fantastic. FluidModeler will help you. Yeah.
Okay.
So just to add, Nelson, like Sam mentioned, it's a concept thing. Now, I don't know if you can see the screen.
Yeah, I can see it.
Okay. So if you look at the screen here, we have the option of giving it a separator condition of this value at this GR, right? So one other trick one can play around that is if you assuming that, okay, here I'll give it the reservoir temperature and set what you have as your bubble point pressure to be this, right?
Yeah.
that's a way to just trick the tool to give you something related. You understand?
Okay. Thanks.
Okay, because of time, I think now this is 15 past of the hour. We've really done well with the timing. If you have any specific question, let us know. We will take it offline. You have our emails address. And if you have concern about, if you want to do like a demo or something, just put your account manager in the loop. Also, add Sofian in the loop, who is the business owner for Reservoir Engineering. Put me in copy as well. We'll make sure that we fix that for you. So at this point, we've come to the end of this section. I want to encourage you to please fill the evaluation from the link that we've sent to you. We really want to get your feedback back. We will process the last 3 videos which you are missing on the YouTube link that we shared with you. We will add them to it. So subscribe to the link as well so that you can get it automatically whenever it is loaded, and you can watch any of these videos later when you need them. Thank you so much for your time, and we look forward to see you again next week.
Thank you, everyone, and have a blessed week ahead. So.
Thank you.
Thank you, everyone.
Thank you all.
Have a good week and stay safe.
Thank you.
Thank you.
everyone.
Thank you, everyone. Thank you.
Thank you, everyone.